Introduction to HCF. Welcome, everyone. Today, we are going to master a very important concept in number theory, finding the highest common factor, or HCF. Now, you might have heard this referred to by another name, the greatest common divisor, or GCD. Regardless of the name, the definition remains the same. When we look at two or more positive integers, the HCF is simply the largest positive integer that can divide into each of those numbers perfectly, without leaving any remainder behind. To find this value efficiently, we aren't just going to guess numbers. Instead, we will use a powerful tool called the fundamental theorem of arithmetic. This theorem allows us to take any number and break it down into its most basic building blocks, which are its prime factors. As we move through today's lesson, I want you to keep this core principle in mind, as it is the secret to solving these problems. The HCF is found by taking the product of the smallest power of each common prime factor that appears in all the numbers we are analyzing. In the next few slides, I will show you exactly how to apply this step-by-step process to find HCF. Now that we understand what the highest common factor actually represents, let's walk through the specific procedure you'll need to follow to find it every single time. I've broken this down into 5 clear steps. First, we start with prime factorization. This means you take each of your given numbers and break them down completely into a product of prime numbers, numbers like 2, 3, 5, and so on, until you can't divide them any further. Second, once you have those strings of prime numbers, you should rewrite them in exponential form. Instead of writing out 2 times 2 times 3, it is much cleaner and more helpful for our next steps to write it as 2 to the power of 2 times 3 to the power of 1. This makes the exponents very easy to see. Third, we need to identify common factors. Look closely at your lists and find the prime numbers that appear in every single number you are analyzing. If a prime number is present in one list but missing from another, we set it aside. It cannot be part of our HCF. Fourth, for those common prime factors we just identified, you must select the lowest power. This is a crucial step. Look at the exponents for each common prime across all your numbers and pick the smallest one. Finally, the 5th step is to calculate the product. Take all those smallest powers we just selected and multiply them together. The final result of this multiplication is your HCF. Keep this process in mind, because in the next few slides, we are going to put these exact steps into practice with some concrete examples. Illustrative example 1. Now that we have understood the theory and the step-by-step process, let's put it into practice with our first illustrative example. Our problem today is to find the highest common factor, or HCF, of 60 and 72. To begin, we follow step 1, which is prime factorization. We need to break both numbers down into their most basic building blocks, their prime factors. For 60, we can express it as 2 times 2 times 3 times 5. For 72, we break it down into 2 times 2 times 2 times 3 times 3. Next, we move to step 2, where we rewrite these factors in exponential form to make them much easier to compare. For 60, instead of writing 2 2's, we write 2 to the power of 2, then multiply by 3 to the power of 1, and finally by 5 to the prime power of 1. For 72, we can simplify its factors into 2 to the power of 3, multiplied by 3 to the power of 2. Keep these exponential forms in mind, because in the next slide, we will use them to identify exactly which factors they share. Illustrative example 1, continued. Now that we have written our numbers in exponential form on the previous slide, let's move on to step 3, where we identify the common factors. Looking at our lists, we can see that the prime factors appearing in both 60 and 72 are 2 and 3. However, please take note. Even though 5 was part of our factorization for 60, it is not a common factor because it does not appear in the factorization of 72. Next, we move to step 4, which is a crucial part of this method, selecting the lowest power. We only care about the prime factors that are shared, and we must choose the smallest exponent for each. For the prime factor 2, we are comparing 2 squared and 2 cubed. The lowest power here is 2 squared. Similarly, for the prime factor 3, we are comparing 3 to the power of 1 and 3 squared. The lowest power is simply 3 to the power of 1. Finally, in step 5, we calculate our final product. To find the HCF of 60 and 72, we multiply our chosen lowest powers together. That gives us 2 squared times 3 to the power of 1, which simplifies to 4 times 3, resulting in a final HCF of 12. This brings us to our next example, where we will apply this exact same logic to a real-world word problem. Illustrative example 2. Imagine a florist who has 48 red roses and 72 white lilies. Her goal is to arrange these flowers into identical bouquets. This means every single bouquet must have the exact same number of roses and the exact same number of lilies, and importantly, she doesn't want to have any flowers left over. The question we need to answer is, what is the maximum number of these identical bouquets she can possibly create? Now, looking at the problem, you might wonder how bouquets relates to the math we just practiced. If we want to divide both 48 and 72 into the largest possible equal groups without any remainders, we are essentially looking for the largest common divisor. Therefore, to find the solution, our strategy will be to find the HCF of 48 and 72. Let's move to the next slide to work through the prime factorization together. Now that we have mastered the step-by-step method using our first 2 examples, let's apply what we've learned to a real-world word problem. Illustrative example 2, continued. Now that we have identified our problem, finding the maximum number of bouquets using the number of roses and lilies, let's move into the actual calculation. We will follow the same systematic steps we used in our first example. First, we begin with step 1, prime factorization. We need to break down both 48 and 72 into their most basic building blocks, which are prime numbers. For 48, we can see it is composed of 2, multiplied by 2, multiplied by 2, multiplied by 2, and finally multiplied by 3. For 72, the breakdown is 2, multiplied by 2, multiplied by 2, multiplied by 3, and another 3. Next, to make our work much cleaner and easier to compare, we move to step 2, writing these in exponential form. Instead of writing out all those repeated multiplications, we use exponents. So, for 48, we can write this as 2 to the power of 4, multiplied by 3 to the power of 1. And for 72, we have 2 to the power of 3, multiplied by 3 to the power of 2. By organizing the numbers this way, we are now perfectly prepared for the next step, where we will identify which of these factors they actually share. Illustrative example 2, continued. Step 3 is to identify the common factors. Looking back at our work for 48 and 72, we can see which prime numbers appear in both lists. We can also see that both numbers share the prime factors 2 and 3. Notice that even though there are more 2's in the factorization of 48, we only care about the ones that are present in both. Next, in step 4, we need to select the lowest power. This is a crucial rule to remember. For the prime factor 2, we have 2 to the power of 4 in 48 and 2 to the power of 3 in 72. To find the HCF, we must choose the smaller exponent, which is 2 to the power of 3. Similarly, for the prime factor 3, we have 3 to the power of 1 in both cases, so our lowest power is simply 3 to the power of 1. Finally, in step 5, we calculate the product. We multiply our chosen powers together, 2 cubed times 3 to the power of 1. When we calculate that, 2 cubed is 8, and 8 times 3 gives us 24. So, to conclude our word problem, the highest common factor of 48 and 72 is 24. This means the florist can create a maximum of 24 identical bouquets, with each bouquet containing the exact same number of roses and lilies. Now that we have written our prime factorizations in exponential form on the previous slide, let's move on to the final steps to solve our florist problem. In the next example, we will see how this same process applies when we are dealing with 3 numbers instead of just 2. Illustrative example 3. Now, let's move on to our third illustrative example, which is slightly different because we are dealing with 3 numbers instead of just 2. Here is the problem. find the highest common factor of 12, 15, and 21. To solve this, we will follow the same systematic approach we used in our previous examples. We'll start with steps 1 and 2 combined, performing the prime factorization and writing the results in exponential form. First, let's look at 12. When we break it down, we get 2 squared multiplied by 3 to the power of 1. Next, for 15, the prime factorization is simply 3 to the power of 1, multiplied by 5 to the power of 1. And finally, for 21, we have 3 to the power of 1, multiplied by 7 to the power of 1. Keep these factorizations in mind, because in the next slide, we will identify which of these prime factors are common to all 3 numbers to find our final answer. Illustrative example 3, continued. Step 3 is to identify the common factors. We need to look at all 3 lists of prime factors and see which prime number appears in every single one. If you look closely, you'll see that the number 2 is only in 12, the number 5 is only in 15, and the number 7 is only in 21. The only prime factor that is present in all 3 numbers is 3. Next, we move to step 4, which is to select the lowest power. In this specific case, the power of 3 is the same for all 3 numbers. It is simply 3 to the power of 1. Since there are no smaller exponents to choose from, our lowest power remains 3 to the power of 1. Finally, in step 5, we calculate the product. Since 3 is our only common prime factor, the highest common factor of 12, 15, and 21 is simply 3 to the power of 1, which equals 3. Now, let's move on to the final step of our third example. Looking back at the previous slide, we have already broken down our 3 numbers, 12, 15, and 21, into their prime factorizations in exponential form. This concludes our worked examples. In the next slide, I will highlight some common pitfalls to watch out for so you can avoid mistakes in your own calculations. Common mistakes to avoid. First, a very frequent error is confusing the HCF with the LCM, or least common multiple. When you are looking for the HCF, you must only take the lowest power of the prime factors. I often see students accidentally taking the highest power instead, which actually gives you the LCM. So please keep this distinction clear in your mind. For HCF, think lowest power. For LCM, think highest power. Second, be careful not to include non-common factors. As we saw in our previous examples, a prime factor must appear in every single number in the set to be considered. If a prime number appears in 2 numbers but is missing from the third, you cannot include it in your HCF calculation. It must be a shared factor across all given numbers. Finally, always double-check your prime factorization for completeness. A common mistake is stopping too early. For instance, if you're factoring 60, you might be tempted to write 60 equals 6 times 10. While that is mathematically true, it is not a prime factorization because 6 and 10 are not prime numbers. You must continue breaking them down until you reach the prime bases, resulting in 2 squared times 3 times 5. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the method, it is very easy to make small mistakes that lead to the wrong answer. If you avoid these 3 traps, you will find this method to be incredibly reliable. Key takeaways. All right, we have reached the end of our lesson. Let's quickly recap the key takeaways to ensure you have a solid grasp of the topic before we wrap up. First, remember that the highest common factor, or HCF, is simply the largest number that can divide all the numbers in a given set exactly, leaving no remainder. Second, we've learned that the prime factorization method is a highly reliable way to find this value. This method involves breaking each number down into its prime components and expressing them using exponents. Third, if you remember nothing else, remember this golden rule. To find the HCF, you must calculate the product of the smallest power of each common prime factor. As we saw in our examples with 60 and 72, we only look at the primes that appear in every single number, and we pick the lowest exponent available. Finally, a quick note on a special case. If you find that there are no prime factors shared between your numbers, then the HCF is simply 1. I hope this method now feels much more intuitive to you. Keep practicing these steps, and you'll be able to tackle even more complex problems with ease.